So the question arose, how do I do question 27? Okay, so 27. Oh, hello. So question 27 says G is a group, and well, it's not very precisely formulated, but it should say that G, little g, is an element of the group, which it doesn't say. Some reason. It should say. And then you can define a mapping called lambda G, which takes elements from the group and spits out elements from the group. And in such a way that pardon? In the way that it multiplies by G, everything. Okay. And you're supposed to prove that lambda G is a permutation.
G and A, are they any two values of G, or is one more constant?
Okay, so the G you fix, and you get lambda G. And for every different G, you get a different mapping, and they're all permutations. Okay? It's kind of a, yeah, so the picture would be, so the picture is this. So you fix some G in the group. And then what you get is, well, you've got all the elements of the group. Well, so the identity is there, G is there, any other A is there. That's G. And you've got the G again. And so the identity is there, the G is there, the A is there, and all the other elements, okay? And each of them is mapped somewhere. So E necessarily goes to G. Yeah, because G times E is G. G goes to G squared, whatever G squared is. A goes to GA. Something goes to A. What goes to A? The inverse of G is part of the answer, yes. Yes, exactly. So the element that goes to A is G inverse A, because if you multiply by G from the left, you get A. Right? So that's a clue to proving that it's onto. Because if you want to prove that suggesting that things are onto any element you pick, you know which one was mapped to it. And so onto should be clear from this. Now, how do you prove that a mapping is injective or one-to-one? So the definition is one-to-one is defined as when you have A and B. No, what am I doing? A and B, there are distinct elements, okay? Then you want to show that the images are also distinct. Yeah, that's the definition of one-to-one. You can't take two different elements and map them to the same, okay? Or this is actually equivalent to when you take the contrapositive. So the contrapositive is lambda g of A equals lambda g of B implies A equals B. Okay, these two implications are equivalent in logic, which you should know from your first year. So I think probably this is the easier bit to prove in this case, and no, it's not immensely hard as the other one. So this is telling you that if G times A equals G times B, okay, then you can, of course, you've got the same element. So when you multiply it by G inverse from the left, you get the same element. So G inverse GA must be G inverse GB. Well, but if you calculate it, then you get that A equals B, and that's equals 1 to 1. So now you just need to write it up nicely and submit it to me. So now, is that clear?
Yeah.
The question, how do I come up with an argument like this?
Yeah, and it was also how the question itself was a bit vague. I wasn't convinced.
I got a bit stuck, yeah.
And the story, I looked at it, I thought I can't do this. I thought I'll ask how to do it.
It's probably nothing to do with your skills, it's got to do with your confidence.
Still wouldn't be able to do that.
No, I mean, the question is not vague. The question is missing that bit of information that G is in G. Yes, that should be there. That is right. But other than that, it's not. I don't think it's vague. Because it tells you that prove that lambda G is a permutation. So what is a permutation? A permutation is defined as a bijection matrix set to itself. So the set is the set of elements of the group G. And you just have to prove that it's bijective, and that's these two things, onto and onto. I can't say that in exactly. Okay, it's just a matter of really analyzing and trying to get to what it actually means to be a permutation. And very often it's just going up to the definition. Okay. So that answers the question. But what we were doing yesterday was this. We were talking about writing permutations as in the forms of cycles like that. Yeah, so cycle is 1 goes to 2, 2 goes to 1, 3 goes to 4, 4 goes to 3. That's the notation that we were looking at, and we ended by the theorem of 9, which says that every permutation can be written as the product of disjoint cycles. And we saw how it works because we saw examples of translating the usual notation in 2 rows of numbers into the cycles. So I got it. Now we want to look at special kind of cycles which are called transpositions. So the definition is that a transposition is a cycle of length 2. Okay, so for example, 3, 5. Well, you don't know what 3, 5 really is because you don't know which group we are in. We don't know how many elements we have. We have at least 5, but it could come from S6, S7, S8, any of the larger symmetric groups. But okay, let's say that it comes from S5. So in the 2-row notation, you'd get 3 goes to 5, 5 goes to 3, and everything else goes to itself. So it's called a transposition because it transposes 2 elements, and that's all it does. Everything else is fixed. Now, the interesting fact about transpositions is that any permutation can be written as the product of some transpositions. So that's well, if it has at least 2 elements. If you have a trivial permutation group on just 1 element, then it cannot be written as a transposition because there's nothing to transpose with, but as long as you have at least S2, then you can do transpositions. Okay, so how does this work? I mean, it's called proposition. It's called proposition 512 in the book. It says that every permutation of a finite set with at least 2 elements can be written as the product of transpositions. Okay, why is that? Okay, so let's have a look. 1, 2, 3. 2, 3, 1. As you can, so this is in the cycle notation. It's 1, 2, 3. Okay, and you can write it as okay, now I shouldn't mess it up. Yeah, 1, 3, 1, 2. No. That doesn't work. What have I done? Oh, it does work. Because we're reading it from the right. Therefore it works. Okay, so where does 1 go in this product? 1 goes to 2. Times this. 2 stays. So 1 goes to 2, so that's correct. 2 goes to 1, goes to 3. 2 goes to 3. 3 stays, goes to 1, so 3 goes to 1. So that actually gives us okay, so and because we're composing from right. That's the convention. That's why I was looking at it and saying, it's not breaking up. This is supposed this is what it's supposed to be, but it's not. Okay, and then if you take a longer cycle, A1, A2, A some K, then you should be able to write it as A1, AN, A1, AN minus 1, A1, AN minus 2, and so on you go. A1, A3, A1, A2. The reason this works is, again, you're going from the right. So you want to know where A1 goes to. Okay, A1 goes to A2, and then A2 doesn't appear again. So A1 goes to A2 as it's supposed to in the cycle. Where does A2 go? A2 goes to A1, goes to A3, and then A3 doesn't appear again in here, so A2 goes to A3. Where does A7 go? Well, A7 goes to A1, goes to A8 in the previous one, and then A8 doesn't appear again, so A7 goes to A8. So this is why it works. So this shows that any cycle can be written as the product of some transpositions. Again, and we had, I can't remember which number it was, but we had this theorem that every permutation can be written as the product of cycles, and therefore through the cycles it can be written as the product of transpositions. And it's theorem 5.9. This is really where the proof starts, isn't it? That was just an example. But theorem 5.9, every permutation is the product of cycles and of transpositions as well. And that's the end of the proof. Okay, so the way you can write a permutation as a product of some transpositions is not always the same. It's not uniquely given from the permutation. You use various ways of doing that. For example, there's the example in the book. So, example 513 shows that the product of transpositions is not necessarily unique. Okay, so the example it gives is that 16253. So this is a permutation written as the product of the joint cycles. You can write it as transpositions, either 162325, but also 1645234525. Are you checking it?
Because font isn't in the cycle itself by putting two sets of the font by cycle two verses.
Yeah, so when you're going like this, 4 switches with 5, and then it switches back, and it doesn't influence anything here in the middle. So, so it's the same. So nothing's the same. The number of transpositions is not the same. The transpositions in it are not the same. However, one thing is the same, and that's the parity of the number of transpositions. So in both cases, there are an odd number of transpositions. And that is, actually, you can't change that. So every permutation comes with this sort of parity. Okay, so it's either an odd permutation or an even permutation. That's what we're heading towards. Now, okay, so the key to prove that there is such a thing as the parity of the permutation, or whatever you want to call it. It's going to be called then the sign, it'll be either +1 or -1, is in the lemma that if the identity is written as tau1, tau2, tau r. Okay, I should probably put is written as a product of transpositions. Then R is even. This is a key lemma. Why is it a key lemma? In proving that there is a parity of permutation.
Is it because it's onto? It's in pair.
What is? Maybe my question is not clear. Okay, so suppose we had this lemma. Okay? What could we do with it? Well, we could say, suppose that you have some element G, and you can write it as sigma 1, sigma 2, sigma r, but you could also write it as T1, tau 1, tau 2, all the way to tau s. Okay. As are two different ways of writing G as the product of transpositions. Okay, so all these sigmas and all these taus are transpositions. But then, okay, another. Perhaps we have not said it. Not said it. But what is the inverse of a transposition? Yes, because when I go back, I mean, that's just an example, but this just switches 3 and 5. If you switch to 3 and 5 again, you get the identity Okay, so multiplying transposition with itself gives you the identity. Okay, so the inverse of the identity is just the identity. Therefore, what is G inverse? Well, it's you take sigma 1, sigma 2, sigma r inverse, right? Now, what does the inverse do with the order of multiplication? Pardon? It reverses it, exactly. Yeah, because that's how it works in a group. I mean, not very hard to show. You've probably done it with Killian. Have you? No? Okay, so it's just, I'll put a note here. When you take GH, okay, multiply it by H inverse, G inverse, you get, well, by associativity, you can do whatever you want first. So GH inverse H, G inverse. So you can do this first, which gives you the identity. So that's the identity. So this shows that this element is the inverse of that element. So that proves that the inversion, what you do is you reverse the order and put the -1 on all of the elements in the bracket. So now here I reverse the order. And I don't put the -1s on them because we've just seen that the inverse of a transposition is the transposition itself. Okay? But then the identity is GG inverse, which is, what have I got? Tau 1 tau S times sigma r all the way down to sigma 1. Is that right?
Yeah, G
So we just see that G inverse is this product of transpositions. G is this product of transpositions. So when I put them next to each other, that's like that. So here I have the identity, or maybe I should be writing id because it's the identity mapping. It doesn't matter. You understand what I mean. So we get, so by lemma, R plus S is even. Because they're even, therefore, they have the same parity. So they either both R and S are even, or both R and S are odd. Okay, so that, now we still haven't proved the lemma, but if we're assuming that the lemma is true, we get what is theorem 515 in the book, which says that, well, it's very wordy, but I should summarize it in a shorter way. So, permutation can either be written as the product of an odd number of transpositions or of an even number of transpositions but not both. Okay, that follows from the lemma. I still owe you the proof for the lemma, but I might just tell you to read it in the book. Because it's long and technical. So, yeah, okay, I'll give it to you. So this is my mark for think about at home. Home reading. Proof of dilemma. What? Induction? Well, yeah, kind of. So from this, we talk of, so that this is not really a definition, but we speak of odd permutations so there's those that can be written as the product of an odd number of transpositions and even permutations. Which are the ones that can be written as the product of an even number of transpositions. And with this, we can have a definition. AN is okay. This comes the subset of Sn formed by what permutations? You're stealing it from the book. So formed by all the something permutations. And the permutations, then the something, sorry, should be either even or odd. Theory. 516. AN is a subgroup of Sn. Now you have enough information to fill in the blank. Why? That is a good reason.
So like it has to be odd.
If it is to be a subgroup, then it needs the identity. And the identity is even, so it has to be even. So the odd permutations don't form a subgroup. That's a good exam question. Prove that all the odd permutations don't form a subgroup. They're all the even permutations. Okay, so proof. In order to be a subgroup, you need, or it suffices to prove two things. One of them is that the identity is there. No. What do you need to prove? To prove that the product of any two elements is still in the subgroup, and what else?
The inverse is also in the subgroup.
And the inverse is also in the subgroup.
Yes.
Okay, so okay, if G is no, permutation should be sigma. Sigma and tau are even. So each of them can be written as an even number of transpositions, the product of an even number of transpositions. Then how many transpositions does sigma times tau have? An even number or an odd number? Well, you take the even number for sigma plus the even number for tau, you get an even number. Okay, so sigma times tau is also even. So that's part one. And then the inverse, if sigma is even, so you can write it as the product of an even number of transpositions. What's the inverse? You can reverse the order of the transpositions. So if it was an even number of transpositions, you just reverse the order, it stays even. So the inverse is also even. Okay, end of proof. So definition continues. AN is called the alternating group. On N letters. It says on N letters, but you can say elements. That's the time. Okay, so it's probably last kind of last note about alternating permutations is the order of the subgroup. So first, as a reminder, what is the order of the symmetric group? Yes. And what is the order of the alternating group? N over 2 factorial. Ah, that's also a guess.
And now I'm going to go back to it's on the bottom of the page. Yeah, you were right.
Yeah, it's n factorial over 2, which says that basically says that it's half of the whole group, symmetric group. Whereas n over 2 factorial, that's a very, very tiny proportion. Okay, why is this? Which is no, it's not theorem. It's called proposition. 517 doesn't matter. 517. Okay, the proof is basically by saying that there are exactly the same number of even permutations as there are odd permutations, and then they must, and because they all together form the symmetric group, and each of them forms exactly half of the elements. Okay? So the proof is that there are exactly the same number of odd permutations in the symmetric group as there are even permutations. So how do you prove that there is exactly the same number of something as there is of something else? No. You can count, but in this case you can't count, and therefore. So how does a small child who doesn't know numbers see if there are the same number of marbles? Oh yeah, exactly. The same number of marbles in two bowls. Oh, there's one left there, so they're not the same number. Okay, so in mathematical notation, this is called a bijection. So if you find a bijection between two sets, then you know that they have the same number of elements. So an, we know what we are. Let bn be the odd be the set of all odd permutations in Sn. Okay, and then and fix a transposition sigma. Okay, this assumes that. So okay, one should put here the note that n has to be at least 2. So if you have permutations of one element, then there's only one permutation, and that's an even one, which is the product of 0 transpositions. But okay, but for at least 2 elements, there is a transposition. You fix that transposition. You look at lambda sigma, which comes back to haunt us from exercise 28, 27. So this to every even permutation assigns an odd permutation because it multiplies it by one transposition, so it changes the number of transpositions from an even number to an odd number. Okay, so this is indeed a mapping that goes from even to odd permutations, and it's a bijection. As question 27 tells us. End of proof. Okay. So in question 27 that this lambda whatever is always a bijection. But now here it has a special form that it's a bijection where it's, where the picture is like this is the whole group, all the elements in the group, and they split into an and bn, the even and the odd permutations. This is Sn. Lambda sigma is a bijection, and moreover, it kind of adds in sort of symmetric way. So it puts all the a-ns onto the b-ns and all the b-ns here. Good. That's exactly what I wanted to cover. So, are there any questions? Next week we'll look at dihedral groups that come in. And see you all on Friday. Hopefully.